Okay, here we go. This is the first video after the apocalypse. So, I want to start off by saying I already have chapters 9 through the end of the semester filmed. So this is the only one I'm going to have to make new. Okay, so I'll be releasing these as the semester goes. Right now we're on chapter 8. That's where we're going to start. Your assignment should be up. I probably will be changing the test date and the due date for all the work, but for now, just start in on your work, and we'll see how we're going as the semester rolls on. But we did lose a week in there, and yeah, we just got to see how it goes. Anyway, what else? What other announcements? I guess that's it. You know how I do. I'll think of them as I go. Anyway, we're going to start off with Chapter 8. Oh, another announcement. That's what I meant to say. The sound might not be that great. You might just have to turn it up because I forgot my microphone. So, yeah, just turn it up if you can't hear. And, and you'll have the slides. I'm going to go ahead and start posting the slides at the beginning of the chapter. I might just post them all now so that you'll have them handy so that you can see everything. You can follow along as I go here. Okay, so let's get going on chapter 8. What are we talking about? I mean, sampling methods and the central limit theorem. Extremely important idea. It's up there. The idea of the central limit theorem is up there with those I was telling you about with that we were talking about as far as the empirical rule goes, and as far as knowing to calculate mean and standard deviation on every single distribution that you see. So it's up there with one of the big ones. It's number 5, I guess, yeah? Okay. So, let's get going. So, sampling methods and the central limit theorem. So, sampling. So, remember where we're at in our statistics class here. Big world of statistics. We have inferential statistics, and we have descriptive statistics. Descriptive statistics were chapters 1 through 4, remember? Probability, chapters 5 and 7, what we just had the test over, that's that's getting into the inferential statistics, even though it's sort of its own little thing, but we are inferring about parameters of a population that we don't know about, usually using the statistics from a sample, okay? Now, from this point on, we're going to be heavy into inferential statistics. Okay, so a lot of what we learned in this last chapter, we'll be able to apply in the last couple chapters. We'll be able to apply for the rest of the semester. Okay, it's just now, instead of thinking about probabilities, what we think is going to happen in the future, we're thinking about proportions. What proportion of the population can we read something about given this sample? Okay, or how can we divide this population up given what we know about the sample we've just taken? Okay. So, unfortunately, I'm going to have to pop out of the camera screen. I don't have a clicker to change this, but whatever. Just follow along. Just listen and follow along when you can't see. Okay. So, reasons for sampling a population. We might have touched on this in your class earlier. By the way, I'm just recording one video for all the sections. So, I'm not going to do this 3 times. One for each section. But anyway, so I don't know if it's something we've touched on specifically, particularly in your class when I mentioned something, but I'm going to assume that we're all to that level now where we can sort of make the leap if you haven't heard an idea explicitly yet. Okay, so why are we going to take a sample instead of utilizing the population? Well, there's several reasons. Okay, so the results of the sample, this is the biggest one. The results of the sample may adequately estimate the value of the population parameter, saving time and money. Okay, so time, money. Okay, like we talked about, I think all the way back. Well, first let's talk about this. It may be too time-consuming to contact all the members of the population, and it may be impossible to check or locate all the members of the population. And the cost of studying all the items in the population may be prohibitive. Okay, so thinking back to the election we talked about at the very beginning of our study of inferential statistics, we we talked about, so the elections tonight, you want to do a survey, you want to do your exit polls, yeah, to predict how the election is going to come out. Okay, is there enough time to contact every person who's voted in the state of Georgia? Remember, we're talking about the Georgia governor's race. No. So we assume there would be, what, 30% turn, 30% of the entire population of the state will have voted for the governor, let's say, okay? Is it possible to contact the 3 million voters in a state as big as Georgia and as disparate, meaning all the way up here in the mountains, all the way down to the swamps, all the way over to the coast, all the way over to Columbus? So it's a big state, isn't it? Plus the city, Atlanta, right? Is it possible? No. Is it too time-consuming? Yes. Is it too expensive? Yes. Okay? So sometimes it's just too prohibitive to do so for one reason or another. Time, money, possibility, the actual logistics of the issue, yeah? Finding all the members of the population, okay? So that's why we take samples. I know we've talked about this before, I think, in all the classes. What about this one? Often testing destroys the sampled item and it cannot be returned to the population. I know I've talked to at least one of my classes about when I was a program manager for the Department of Defense, and sometimes we would have to destroy the items that we were testing, okay? So you can't really destroy your whole population, can you? So the destructive nature of the test limits how many of the items you can test, doesn't it? You can't just destroy them all, then you wouldn't have any population left at all. You're taking each one that you test out of the population, aren't you? Okay. So that's why we would sample, and I think you've been exposed to that before, and I think we've talked about it before. So let's skip on to the next slide. Okay. So we have several methods for sampling, okay, and they each sort of add a wrinkle, get a little more complex as we go, but let's talk about them one by one, and it'll make a lot of sense. This first one, simple random sampling. The most widely used method of sampling is simple random sample, and this is what we think about when we think about sampling, don't we? So, sample selected so that each item or person in the population has the same chance of being selected. What does that mean? It means just what it says. There's an even chance of being selected. How would we assure that happens? Well, what about when you pick a name out of a hat? Let's say we give everybody the same size piece of paper, give everybody the same pen or pencil to write on, whatever. They write their name on it, throw it in a hat, shake it up, and there's an even chance that each name is going to be drawn, is there not? So we're talking about random, simple random sample. Let's look at these example right here. So always these examples are really going to come in handy for you now that I'm not here to walk you through them. Just take the time to read through these examples because I think the book does a really good job of using clear, concise, easy examples, okay? But let's talk about it. There were 750 Major League Baseball players at the end of the 26th season. A committee of 10 players is to be formed to study the issue of concussions in baseball. I did not know concussions were such a big deal in baseball, but anyway, maybe I guess stealing home or running into the catcher, that's all I could think of. But anyway, to make sure every player has an equal chance of being selected, write a name on a piece of paper. That's what we were just talking about. Place the names in a box and mix them up, draw 10 names. So they need 10 out of the 750 players. And so there's an even chance of each one of those 750 being picked, aren't they, to constitute that committee of 10. Okay, so simple random sample, not that complex. We can add a step to it. That step being, we can use a table of random numbers, and I know from looking in the back of our book, at the chart in the back of our book, that all the other tables we've looked at, there is one back there you might have seen. But using the same example, suppose we got to pick the same 10 players. So prepare a list of all the players and number them 1 through 750. Okay, so we have numbers 1 through 750. So the 750 is the largest number we have, isn't it? So 750, 3 digits in that number. So we're going to pick a place in this table of random numbers, and we're going to come up with a pattern. So we're going to pick 2 here, skip 2, pick 2, skip 2. Of the third row down, the first 3 in the column. Okay? So these 2 are skipped. We're going to pick 037 from here, 447 from here, skip 2, 189 from there. The starting player, second player, third player, hold up. Hold on just a second. I think I just touched the board, and that's why I did that. So project from PC, I'm guessing that's what we want. Yeah, shoot. No signal from the computer. Hold up, I've never used this. I don't know. There it is. Okay. So suppose so everybody got this, right? So we would find the name that matches up with 037 with 447, etc. Okay. Now let's step it up one notch with systematic random sampling. Okay? So if you don't have a list of the entire population to begin with, you can use systematic random sampling. You have a random starting point that's selected, and then every k member of the population is selected. Okay? We're talking about in this grocery store example. Studs wants to know the length of time customers spend in their store. Randomly select the days of the week, time, starting point of the study, and systematically select customers and measure the time each spends in the store. So there's a system. We didn't just pull the ones we thought were appealing or we thought were nice. We had a system, we followed it. Every 12th customer we followed, yeah? Okay. Or survey. Okay. This is the third type, okay, of sampling, and it's still randomized sampling, but we're going to step it up. We're going to stratify our sampling, okay? Now this is going to be good for ensuring that we have a representative sample when we have disparate, spread out information, okay? And we have low probabilities of one group or another being utilized in the sample, yet we want them in the sample to be represented, okay? So let's look at this. When the population can be divided and reduced based on some characteristic, use stratified random sampling. Okay, population divided into subgroups called strata, stratified, strata. Any sample is randomly selected from each stratum, singular plural. Okay, so a study of 50 of the largest 352 U.S. companies and their ad spend, how much they spend on advertisements. Okay, so we begin by identifying the strata, and then we sample within each stratum to get the representative sample that we want. So let's have a look at this chart. I don't know if you can see it on the video here, but you have it. You should have it in front of you, okay, on your computer. Okay, so we have 5 strata here, if you can see the chart, and here's how we split it up. Here's how we split up all those 352 companies. 50 companies. No, 352 companies. No, 50 that we sampled, okay? So we split up by profitability, 30% and over, 20 to 30%, 10 to 20%, 0 to 10%, and then a deficit. What are those percentages? That's their return on investment. That's their ROI on their advertising spend. So this means, this 30% and over means for every dollar they spent, they made at least $1.30 back in advertising, in revenue due to the advertising. How they track that it's due to the advertising, I don't know what their internal metrics are, but this says what they would have reported on their 10Ks. These are probably publicly traded companies, so that information is available. Yeah? All right, because they're the 352 largest firms in the U.S. All right, so from there we build a frequency table. Remember that? Didn't think we'd see those again, did you? But they're never going away. All right, so in stratum 1, 30% and over, 8 firms out of the 352. Don't move. I came too close to it. 8 out of the 352 made 30% or more return on investment on each dollar they spent on advertising. Okay. The ones that made 20 to 30%, 35 out of 352. That's almost 10%, isn't it? Okay. What about 10 to 20%? That's the big chunk of it. 189 out of the 352. Over half made 10 to 20% on their advertising spend. Okay. Returned the profitability on their advertising spend. Okay. Now, what we do with that is take it to we build a relative frequency table out of that. So So you remember doing that? This is the same steps we've done 100 times before, okay? So we have 8 of the 352. 8 divided by 352 is 0.2. So about 2% of the firms made 30% or more on their advertising spend, okay? And then about 10%, 35 out of 352, return 20 to 30%. 35 divided by 352. We know that's about 10%. Rounded, don't we? Okay? So, we get all those relative frequencies together, don't we? And then we multiply the relative frequency by the number sampled. So, we know what the relative frequency is, don't we? We just calculated it, and we know what the number that we're going to sample out of that 352 is in the problem. It's 50. So you have 50 of the 352 largest. So we can identify out of each stratum how many we need to pull in our sample. So within each stratum, we're going to randomize our sample. So within the first one, we're going to do a box. And we're going to have all 8 of those companies written on a piece of paper. And we're going to shake it up and pull how many? 1 out of those 8. Okay? Because we know that 2% of our study needs to be within this stratum, the 30% or over. How do we know that? By the population, by looking at the population and how we divided it. Okay? So essentially we're applying those population proportions to the sample proportion. Therefore, we make sure each stratum is represented proportionally. Okay? So number sample 1, we do the same thing here. Now, 10% of 50 is 5, isn't it? 54%, remember 189 is over half of 352 we said, so that's about right, yeah, 54%. So 27 is about 54% of 50. Okay? 0 to 10%, 115 is about a third of 352. 16 is about a third of 50, isn't it? So see how that the proportion in the sample is representative of the proportion in the population. Therefore, we can ensure that each group is represented proportionally. All right. And the last is cluster sampling. This one, you really don't have to draw anything out because it's already drawn out for you. Okay, so this is taking natural boundaries, frequently represented in geographic bounds, and sampling within the already drawn out delimiters, parameters. Okay, so cluster sampling, common type of sampling used to reduce the cost of sampling over large geographic areas. This is what it's mostly known for. Populations divided into clusters using naturally occurring geographic or other boundaries. Then clusters are randomly selected and samples collected by randomly selecting from each cluster. Okay. Okay, so that's about it for sampling. The most common form by far is simple random sampling. But stratified sampling, stratified random sampling can, though it's a little more complex, can be one of your best friends in business because, like I said, you get a more accurate representation of your underlying population. Most of the time. You have to be able to decide when to use which. Okay? Okay, that's it for sampling. Now, the sampling error, what are we talking about? So, we're going to have a couple terms in here that both involve error. Okay? And by error, what I'm talking about is the difference between a parameter and a statistic. So, remember what those are. Your parameters are your characteristics of the population. Your statistics are characteristics of the sample that you pulled from the population. Okay? So your parameters are always going to be the real deal, aren't they? The only reason we're pulling the sample is so that we can find out something about the underlying population. Okay? So that error, what we're talking about, is the difference in what we find from our sample in regard to the population. So it's literally that difference between the statistic of the sample and the corresponding population. So for each of these characteristics of populations and means of data sets that we've talked about, all the characteristics, meaning all the measures of location, all the measures of spread, all those different measures that we talked about, the dispersion, remember? Okay, they each have a corresponding statistic in the sample, don't they? They're going to. We could calculate those, couldn't we? Okay, and so each one of those characteristics is also going to have an error. All right. Now, the difference between a sample statistics and a corresponding population parameter. That's the official definition. Again, nice, clean, concise definition, so just keep it in mind, okay? Now, there's the sampling error. We're also going to look at something a little bit later called the standard error. Please do not confuse the two, okay? And we'll get to the standard error in a little bit, but the sampling error is just an overall sort of just a word put to a simple idea, okay? The standard error is something extremely specific, okay, that we're going to get to a little bit later on today. Okay, but let's move on from that. So it's unlikely that the mean of a sample, so the mean, that's one measure of location we looked at, right? So if we were to calculate the mean of a sample, it's unlikely that it'll be exactly equal to the population mean, isn't it? So it's rare that we'll pull a sample from a population that gives us the exact statistics that match the parameter, isn't it? Okay? Let's look at an example. The Foxtrot Inn's number of rooms rented in June. The mean number of rooms rented is 3.13. So we have June 1st through the 10th, 11th through the 20th, 21st through the 30th right here. And it has the number of rooms rented. Okay, again, you're going to have to pull this chart up. I know it's a little bit small on the video, probably for you, but you'll have the slides. So just pull it up and follow along. Okay, so if we average all these out, all these 30 days out, for the number of rooms rented, we get an average, a mean of mu, remember, Greek population, yeah, of 3.13. All right? But now let's take 3 random samples, just easy, simple, random samples, yeah? Of 5 of the 30. Let's do that 3 times. Let's average 5, let's average 5, and let's average 5 again. And we get 3 different X bars, Latin, remember? We get 3 different sample means, don't we? 3.8, 3.8, 3.4, and 1.8. Okay? None of those are the exact same as 3.13, are they? They're all different from 3.13, yet they came from the population whose mean is 3.13. So the sampling error is the difference between each X bar and mu. Why does it keep doing that? I'm not even touching it. Okay, so, for instance, the first one, the sampling error is going to be, I'm not even touching this thing, it's freaking out on me. The sampling error is going to be 0.67, isn't it? See, I didn't do that. Okay. The second one, the sampling error is going to be 0.27, yeah? And the third one's going to be 0.33, yeah? Okay. The positive 0.33, negative 0.27, and negative, because well, it depends on how you look at it. But that's just the difference, okay? All right. The sampling error. Okay, so, let's stick on this example for just a second. Let me ask you something about this. Okay, so what we've done right here is we've taken 3 samples of 5 each, haven't we? Okay. Let me ask you this, though. What if we were to keep taking samples of 5? We did 4, and then we did number 5 samples of 5, and we got the mean, and then 6, and then 7. And what if we did that as many times as possible? What I'm saying is, remember when we did the combinations and permutations? Okay, this would be combination, wouldn't it? Because the order doesn't really matter. A group of 5 is a group of 5. So what if we did that as many times, the combination of 5 as many times as we could, and we got, what is that? Okay, and we We averaged them. And then we averaged the averages. What do you think that mean would be? So what I'm saying is we did it not just 3 times, but we did it, I don't know how many times it would be, but let's say 300 times we could do it. We could take groups of 5 and get a new mean for each group of 5. We could do it 300 different ways using those different numbers. We did it the maximum number of ways possible. And then we had all these different means, 3.8, 3.4, and 297 other ones. And then we averaged all those averages together. What do you think the answer would be? If you guessed 3.13, you would be right. And why is that? It's because 3.3 is the mean of the underlying population. We took every single combination possible of samples from that underlying population and averaged them together, didn't we? So it only makes sense that our final average from all those different samples would be the same as the underlying population. We used we exhausted every single combination of sample averages we could do, and then we average them together. It would make sense that it reflects the underlying population, doesn't it? It'd be a lot of math, but we would come up with that same answer, wouldn't we? Okay. If you understand what I'm saying, that's a really important idea, and it's called the sampling distribution of the sample mean. Okay? All right, extremely important idea because it's going to underpin the big idea that we're going to have next, okay, that we're going to talk about next, okay? Well, for now, we have to understand how this works. Now, I'm not going to pull it up right here, but I'm going to add a separate video. I'll add it at the same time as I add this today. A cool little program online that I found that really draws out how this works, okay? And so I'll put that on just with this. But I'm not going to stop now. We're just going to talk this out and see if we can get it. Then you can pause the video and go to my sample that I'm going to show you online, the other video that I'm going to have with the online program that really draws this out if you don't get it. And then we'll move on to the next big idea. Okay, so how can we determine how accurate the sample mean is? Sampling distribution is sample mean, a probability distribution of all possible means of a given sample size. Again, in that last example, our given sample size was 5, wasn't it? Okay, so we took groups of 5, as many groups of 5 as possible in every different combination, and averaged them all together, didn't we? Averaged each of those averages, and we got the underlying population average for an answer. So for a given sample size, the mean of all possible sample means selected from population is equal to the population mean. Makes sense, doesn't it? These are one and the same, aren't they? Samples just come from populations, right? And so it makes sense that if you use every single combination, every single version of a sample from a population, it will give you the parameters of the population. Okay? There's less variation in the distribution of the sample than the mean of the population distribution, and the sampling distribution of the sampling mean tends to become bell-shaped. That's the big idea right there at the bottom. So what that's saying is, so we have our underlying population distribution. I just pulled this marker out new. Okay. So we have our underlying population distribution, is what it's saying, yeah? And we're going to pull the first sample of 5, for instance. This is the 30 days. Or this is something, but we know it's normal, don't we? Because remember, our data is grouping in the middle. But we do a sample of 5, let's say, and we get an answer there. And then we mean there. And then we do another one, we get an next bar there. And then we do another one, we get an next bar here. We get one here, and we get one out here. But they're going to start to accumulate around the mean, aren't they? Why is that? It's not just because they're attracted to the mean. The mean is the mean because the data makes it the mean. Remember, it's a chicken and the egg situation. But what you're eventually going to have is something that looks like this. Usually, it's going to be taller. This is the sampling distribution of the sample mean. Because again, each one of these X bars is a mean of a sample pulled from the underlying population. Okay? So if this is the underlying population, your sampling distribution and your sample mean is usually going to be taller and skinnier, isn't it? Because you're taking means from the sample. All right, so those means are more likely to fall in the middle, aren't they? And as more fall in the middle, it shoots up this data, doesn't it? Okay? Now, what's really interesting, first let's do an example here, okay? I think there's an example on the next slide, and there is. Okay. So sampling distribution example. TARDIS Industries. Hold up a second. Yeah, we're good. TARDIS Industries has 7 production employees. That's the entire population of their production staff, okay? The hourly earnings of each employee is given in the table. The table down here below. Hopefully you can see it. It's a little bit bigger. If not, again, you have the slides. What's the population mean? 2. What's the sampling distribution of the sample mean for sample size of 2? Given the sample size, aren't we? What's the mean of the sampling distribution, and what observations can be made about the population and the sampling distribution? Okay. So question 1, what's the population mean? How are we going to figure that out? Well, we're going to add them all up and divide by the sample size, aren't we? Or the population size, in this case. Uppercase N, remember? Nu. Yeah? And we're solving for mu, aren't we? Population is what we're dealing with here, okay? So we have Joe, Sam, Sue, Bob, Jan, Art, and Ted with their hourly earnings. We add them all up, divide by 7, we get $15.43 an hour as the average earnings at TARDIS Industries for the production employees. Okay? What's the sampling distribution of the sample mean for the sample size of 2? Okay, so what are we going to do? We're going to take every single iteration, every single combination of 2, and we're going to average them together, and then we're going to average all the averages. Okay? So how many ways are there to calculate a sample size of 2? Well, remember, we do have our combination formula, don't we? It would be 2C7, wouldn't it? But it's drawn out for us here. Okay, so first we have Joe and Sam, right? When we average theirs together, their earnings, so Joe makes 14, Sam makes 14. So Joe makes 14, Sam makes 14. We add them together, divide by 2, the mean is 14. Does everybody see that? Okay. We do that for each of those. What about Joe and Sue together? Now we're going to have Sue and Joe together? No, we're not going to repeat them, are they? It's a combination. Order does not matter, okay? All right, so we have Joe and Sue together. That means Joe and Sam are the same as Sam and Joe, right? Okay. Just in case you don't remember. I know that was a few chapters ago. So, Joe and Sue. Joe makes 14, Sue makes 16. We add those together. We get 30 divided by 2. Our average is 15. Okay, so we're going to do that with every single combination, every single possible combination. Okay, and that is the sampling distribution for the sample size of 2 of the mean. Okay, we can also do this with standard deviations. We can do it with anything, but the mean is the most common, isn't it? Because remember, every time we find what? Mean standard deviation. Doesn't matter. It's popped in your head automatically. Okay, what's the mean of the sampling distribution? So, how are we going to figure this out? So, sum of all the sample means is 324. We have 21 samples. So, the mean of our sampling distribution is $15.43. Does that look familiar to anybody? What was our population mean? $15.43. What is the mean of the sampling distribution? $15.43. And why is that? I think that's question number 4. What does it say? Yeah, what observations can be made? So the mean of the distribution, of the sample mean is equal to the mean of the population. Okay, so the spread is less than the spread of the population values, and the shape of the population is different. Okay, so what just happened there? So again, we had this to start out with. By the way, we're going to make another important point here. This is a normal curve. Is this a normal curve that we started with from the underlying population? We'll get to that in just a second. But anyway, what happened with this one, remember? It got sucked in the middle, didn't it? And it's taller and skinnier than the other one. than the underlying population. The spread in the distribution of the sample is less than the spread of the population value. Same here. The spread is smaller, isn't it? Okay, the dispersion is less. And the shapes are different. So how are the shapes different? So it's dispersion, first off, is the dispersion less here, 14 to 17 there, 14 to 18 there. So it is, isn't it? Okay? But let me ask you one other thing. And by the way, these are just as tall as they are represented in the sampling distribution, aren't they? Okay? But let me ask you something else here. Does this look normal? Does this look like a normal curve? It really doesn't, does it? Well, let me ask you, after we did the distribution of the sample mean, the sampling distribution of the sample mean, does it look a little more normal now? I would argue yes. This looks a little more like a normal curve, doesn't it, than that? We might be onto something. Could there be more to this? And I'm going to tell you right now that yes, there is. Okay. What we've done right here is shown how an underlying distribution that is not normal, this is not a normal distribution, is it? Can be turned into a normal distribution using the sampling distribution of the sample mean. Why is that important? That is important because look at everything we've done with normal curves so far, just even in the last 2 chapters. That's a lot of stuff that we can do with a data set that's normal, isn't it? That we can't necessarily do with data sets that are not normal. Okay? But if we can take a data set that is not normal and turn it into a normal distribution, we can then utilize all the tools that we know how to use on a normal distribution on that non-normal distribution. Okay? What I'm saying is this. This distribution that we just looked at, these generic numbers here, yeah? If it looked like this, that is not a normal distribution, is it? But do you think that could happen in business? Life frequently? Yes, it can. Not everything works out just perfectly like that. Like a normal distribution, like that bell curve, does it? But using the sampling distribution of the sample mean, taking all those different samples and averaging them up, we can turn this into this. And when we do that, we can utilize all the tools that we've learned. What about the empirical rule? All that kind of stuff, yeah? We can use our z-score and figure out areas under the curve. We can do all kinds of stuff, can't we, that we've learned about with a we can only do with normal distributions. Okay, so that's the beauty of this, and there's a name for this. It is called the, drum roll, one of the most important ideas you'll learn in this class, the central limit theorem. Okay? The central limit theorem. Like I said, this is one of the big, now we have 5. I can't remember the others that I told you, but this is add this to the big 4. Okay. If samples of a particular size are selected from any population, doesn't say any normal population, doesn't it? Does it? Normal distribution. The sampling distribution of the sample mean is approximately a normal distribution. The approximation improves with larger samples. Okay, that second line is important. So what that means is you can't take an ugly distribution like this and make it a normal distribution with a tiny little sample. Okay, it's going to take larger sample sizes. What are those? The general guidelines are this. If the population follows a normal probability distribution, then for any sample size at all, the sampling distribution of the sample mean will also be normal, which makes sense. The underlying population is already normal. You're not going to make it unnormal by, not normal, by taking a sample from that underlying normal population, aren't you? Okay? We're turning them into normal distributions. We're not, this doesn't go in reverse, okay? So if the population distribution is symmetrical, You'll see the normal shape of the distribution of the sample mean emerge with samples as small as 10. What does that mean? Remember these? What are these called? Remember that? That's a uniform distribution, isn't it? We start taking the means, we can turn one of those into it. What about these? What is this one called? Bimodal. Remember this one? Well, we can turn that into a normal probability distribution. Again, what's the benefit of this? We can use all those tools that we've learned so far, and that we're going to continue to learn, by the way. We're just getting started on that. But we can use all those tools on this distribution, on this data set after that, okay? And if the distribution is skewed or has thick tails or looks like this, something funky, yeah, then it may require samples of 30 or more to observe the normality feature. Now, this is the point where I would stop and look at the other video, okay? And at the sampling distribution of the sample mean software, and I'll run through a quick example that's really cool and it illustrates it well. In fact, I'm going to stop the video right now so you can have a chance. Okay, so picking back up with the central limit theorem. So here's a nice chart of what I'm talking about with the sample sizes and what it's going to take in order to turn these distributions, these different types of distributions, into normal distributions in order to be able to make some sense out of them, essentially. Okay? Okay, so again, a bimodal distribution, sample size of 2, yeah, it's still going to be, remember, our normal curves, remember, all the characteristics hold, yeah? They're divided in half by the mean, median, and mode, remember that? Half on this side, half on that side. They are asymptotic, so all those characteristics still stand, yeah? Okay, so, again, you have this bimodal distribution. What's going to happen? It's still, symmetrical, yeah, with a sample size of 2, but it doesn't have that normal shape. What's happening here? It actually is inverted, isn't it? We're peaking in the middle already with a sample size of 2. And again, this is every single possible combination of 2 from that sample, from a sample combination of 2 from the population. Now what's happening with a sample size of 6? That's looking normal, but look at 30 down here. That is what we're after, okay? That is going to be way more accurate than any of the rest of them, all right? And the same thing with the rest of them. Here's our uniform distribution. Here's something skewed way to the left over here at the end. Here's something skewed, or way skewed to the right. Here's something skewed to the left up here on in the second one. So you can see as our sample size increases, we start looking a little more and more like this, don't we? And that's what we're after with sample distribution and sample mean for our most accurate normal distributions. It's going to give us that we can most effectively utilize our tools on. Yeah. All right. So central limit theorem conclusions. The mean of the distribution of sample means will be exactly equal to the population mean. Again, the means are when we take as many combinations as we can that's possible, average them all together, or get the average of each and then average all those averages together, it's going to equal the population mean, isn't it? Which only makes sense. If you really think about it, that's the only logical conclusion you can come up with, isn't it? Because it is the underlying population at that point. It's not really a sample anymore, is it? We're utilizing every part of the population. It is the population, just expressed in a different way. Okay, so the standard deviation of sample distribution sampling is also called the standard error of the mean. Okay? And all we're really talking about with the standard error of the mean is the standard deviation of those samples all put together. So it's not the standard deviation of the population, and it's not the standard deviation of one sample, is it? It's the standard deviation of all those samples put together. Why is it going to be different? Well, let's think about this. What are we looking at than the population mean or than any one single sample, than the population standard deviation or any one single sample standard deviation. Why is it going to be different? Well, let's think about it. What are we looking at right here? What is the standard deviation? It's a measure of dispersion, isn't it? What is this dispersion? What does the spread look like on this new normal curve that we've created out of this underlying data? Remember, it's skinnier and it's taller, isn't it? So our spread is not going to be as wide, is it? So let's look at the formula. Why do you think that makes sense? So what is our formula for the standard error of the mean? It's sigma, okay, which is the standard deviation of population, isn't it? Divided by the square root of the sample size. Okay? So, I've been harping on this Greek-Latin stuff, haven't I? All semester. Well, here is a good example of why that's important. Because what are we talking about here? We're talking about the population standard deviation divided by the square root of the sample size, aren't we? We're using the population and the sample in the same formula, aren't we? Okay? To represent the standard deviation of the sampling distribution of the sample mean. Okay? I'm just trying to show the spread is not as wide. Okay? Which makes sense that it's not going to be as wide as the population standard deviation, is it? Because it's divided by something. When you divide something, remember, when you divide a number, it's going to be smaller than the number itself, isn't it? And why is that? Because you're dividing up into parts, aren't you? Okay, so here we're dividing. We're putting the standard deviation of the population into terms of the sample size, okay? Just think of it like that. Why is the square root of the sample size? Because we're talking about standard deviation, aren't we? We're not talking about the variance, are we? Okay, but don't overthink it. Just remember that formula. That's probably number 6, actually, that you can't forget, okay? The standard error of the mean. Sigma divided by the square root of n, not nu, n, okay? How are we going to use this new formula? Well, remember our z-score formula. Remember that z-score that allows us to find the area under a normal curve, no matter what that normal curve looks like. If it's a normal probability distribution, it's going to hold to our z-table, isn't it? Remember? And that z-table goes ahead and calculates this area under the curve given this curved line, doesn't it? Remember, we don't have to do that, do we? It's the same for every single normal distribution, isn't it? We just pick it up, move it onto the z-scale. It's the same data, remember? We got the underworld down here, yeah? That's the z-data. This is the real data, okay? Okay, so, but our new z formula, given that it's not a sample or a population distribution, but it's the sampling distribution of the sample mean, we're going to put the standard deviation of the sampling distribution of the sample mean as our denominator, aren't we? Remember our old formula, which is z equals x bar minus mu over sigma. Now, we're going to put a sigma divided by the square root of n, because precisely what we have done is reframed that denominator, that sigma, into the terms of the sample size. Okay? All right. So other than that, it's the same formula. And we can figure out, we can do all the same stuff we were doing in Chapter 7 with the z-score. Everything else about the z-score is the same. We use the same table, everything. It's just that denominator is going to change when we're talking about a normal probability distribution graph that's made like this, with the standard, with the sampling distribution of the sample mean. And I keep saying mean because that's where we're going to stay for this chapter. We're not going to look at other statistics or parameters, okay? All right. So, hopefully you see the power of the central limit here. Hopefully you understand what I'm talking about with sampling distribution of the sample mean, why it's significant, but most of all, that central limit theorem, why that is a real game changer, okay? And hopefully you can do all the different types of sampling we looked at, especially that stratified that stratified sampling, that's the most important one, I would say. That's going to be the hardest one for you to do on your homework, but it should be fine. You do a couple of those, you get the hang of it, and it's actually a really nice tool that you'll be able to use for the rest of your life in business and other places, okay? But you got to get the central limit theorem. You got to understand what we're talking about here, okay? So that's it for chapter 8. Now, like I said, the rest of the videos are going to be, I've already filmed them. So you might hear some stuff in there that's not talking about your class. For instance, I had different chapters on the test last semester. I did 8, 9, and 10. We're only going to have 8 and 9 on this next test, okay? So you'll hear stuff like that, but you don't need to email me and say, hey, I thought we only have 8 and 9, because those videos were filmed last semester. So, but the information is the same. The actual class information is the same, okay? All right, so email me if you have any questions. Watch this video. Watch the video I'm putting on with this. And stay healthy. And I'll see you next semester. Or next video, whatever.